Okay, so good morning. So let's wake up and let's start today's class. So this is 17. So today I want to just change the topic from the last class. In the previous classes, we were talking about faults and then how to solve that. And today I want to generally talk about optimization. So optimization is actually a complete course altogether with a lot of lectures. But here we'll just, instead of having full length course on this, we'll just try to summarize it in just one lecture, just the basics of it. So what might be needed for us in future. So just a minute. Okay. So I will start by saying what are the applications. So have you heard about this topic before? Have you studied this topic somewhere? Optimization. What? We used where? Simplex method. What about others? I was just trying to get an idea whether you have studied this subject before or something new. So looks like it is something new. So what are the applications? So I'll just return some applications of optimization. So a lot of applications are there, mainly in the designing. So I'll just quickly give some of the examples. So designing of electrical machines. If you want to design an electrical machine, you will use some optimization in that. So design of electrical networks. So you want to minimize production cost. So how to minimize the production cost in a factory. Design of mechanical components, design of water supply pipelines, some oil refinery kind of things, some civil engineering, space applications, aircrafts, and this kind of lot of fields we use optimization. So there are only main two steps in general. One is the formulation. So and the second one is the solving itself. So any problem you have to formulate it as an optimization problem, and then the second step will be solving it. So usually this is done by humans, and usually this is done by computers. So for solving, better to use computers. Now the problem is, for computers to be able to understand the problem and find out the solution and all, you have to give the input to the computer in a standard format, in a specific way. So that's what is the formulation of your optimization problem. So in optimization, what you are trying to do, I'll just give you the general what you call the general form of formulating an optimization problem. You will have something like minimize, and then there is a function f of x. So this x is a vector actually. It's not. It has x1, x2, x3 like that. So I want to minimize this function. The value of that function I want to reduce as much as possible, and then subject to some constraints. Let's call it g of x equal to 0. So let's say g I, and then so like this. So there are some constraints. So again, this x may be x1, x2, x3, like number of variables, and this is equal to 0. That is, we are assigning some conditions on the values of x. Similarly, this is equality condition, this is inequality condition. So, given this kind of problem, finding out, so x can be x1, x2, x3, that means multiple unknowns. So, you don't know what is the value of this x. So, x1, if you take only two variables, two dimension kind of thing, then it is x1, x2. So, you don't know x1, you don't know x2. Find out the best value of x1, x2 so that this function is minimum, like that. So, this is called objective function, and this is called equality constraint, and then this is inequality constraint. So, this is constraints. So, and this whole thing is nothing but the formulation. So, any problem is given to you, normally it is explained in terms of engineering language or in English language and all. You have to identify what is your unknowns, and once you identify your unknown values, you have to identify what is your function, and once you identify what is your function, then you have to identify what are the constraints, and then once you identify the constraints, then all that you write it in a standard form, then your first step is over, formulation is completed, and then second step is solving it and then finding out the solution. I'll give you one quick example. Today we will not see much of electrical or power system kind of problems. We will see general problems, and in the next class we will see optimal power flow, which is application of optimization for power systems. One of the examples. So let's continue this. So I'll give you one simple question. So you might work on it. So the question is something like this. Let's say there is a this is a river. This entire is a river, and this is the land. So I want to construct a fence like this. So this is a fence. I want to construct a fence like this. So this is total length is this one. So the total length I have is let's say 240 meters. Okay. I have 240 meters of this material, this rectangular this thing, and I want to construct this side. It is not required because anyway it is river. So three sides I want to construct the fence. Total length is 240, and I want to cover maximum area. Well, I want to cover the maximum area within that. Okay. So the question is now, how will you construct that? What is the design for your fencing? So now let's try the this one. So here minimize f of x. So if you want to minimize some function, if you take minus of that function, that means you want to maximize that function. So minimize and maximize are there's no two separate problems. If your computer program you have written and it can only solve minimization problem, the same computer program you can use it to solve the maximization problem also. Just reverse the sign of your objective function, the same program will work. So that's why we only worry about one case. So here I want to maximize the area. Maximize area. So what is the A value then? So here what are the variables? Length and breadth. Okay. So let's call this B, and then this let's call that L. Okay. So what is the area now? L into B. So nothing but L into B. So I want to maximize L into B. Okay. And what is the constraint? What? So L plus 2B equal to 0. So this is the equality constraint, G like this. Okay. Is there any inequality constraint? There is no inequality constraint. What? Oh, sorry. Is equal to 240. Yeah, we can. So, but here if you want to keep it right is equal to 0, you can put minus 240 equal to 0. So for the timing, we'll leave it like this. So there is no other inequality constraint. So that's all. This is a formulation. Maximize this one subject to this one constraint. So what is your next step? How will you solve it? Now let's go to the solving part. Okay, if you want to solve it, how will you solve it? Okay, so L equal to 240 minus 2b. Okay, then A equal to 240 minus 2b into b, and A equal to 240b minus 2b square. So this one I want to maximize. So what is the next step? Yeah, so you might have seen that a lot of times before. When you want to find out the maximum value or minimum value of a function, simply take the derivative and equate it to 0. So derivative of A with respect to B. So what is that? 240 minus 4b equal to 0. So this equal to 0 we are adding. Okay, so what is B? 240 divided by 4. Okay, 60. So what is L? So L is here, 120. Okay, so you should design this one in such a way that this is 60, this is 120, and this is 60. In that case, the area is maximum. So how much is the area? 60 into 120. Okay, so our area is coming 720 meters square. Okay, so if you make it 61, what will happen? If this is 61, this will also become 61, and this will be 118. Okay, in that case, what is the area? So I'll write area minus because we are reducing the length, or just we'll calculate the area now. What is that? 61 into 118. How much is this? Can someone quickly try that? 61 into 118. You have calculators? 719. Is that correct? It should end in 8. 1 into 8. Is it 718? How much? 7198. This is 7200. Okay, 7198. Okay, so this is more, this is less. That means slightly if I increase the B, I am getting a lesser area. Okay, slightly if I reduce the B, so if I make this 59, this will become 59 and this will become 122. Okay, so what is area now? 59 into 122. How much is this? 59 into 122? 7198? Is that same? So if I increase it, the area is reducing. If I decrease it, the area is reducing. Whatever the value that was there, that is the giving you the maximum value. So if even if you want to minimize some function, you will still do the same thing. Differentiate and equal to 0. You can minimize the function or you can maximize the function. But how do you know whether it is minimized or maximized? So take the second derivative. So you might have already seen that. So what is d2a by db2? So this one, right? Minus 4. Okay, because this is second derivative is negative, your value will be maximum. Okay, so do we have? Okay, just for a little more practice for the people who have just come, let's do one more quick problem. So this time the problem is like this. let's say I want to design a cylindrical container. Okay, so a container in the form of cylinder. Okay, and the capacity is let's say 2 liters, or I will say 2000 centimeter cube. Okay, so this is the volume of that. Okay, so how do you design the cylindrical? It consists of what? There will be a base, which is this one. There will be a top, and then there will be a cylinder. Okay, so designing this one using less material. So how will you do that? Yes.
How this problem is related to power?
In power, in fact, the optimization has a lot of advantages, a lot of applications in various fields. So in this problem exactly may not be directly related, but in power system there is a problem like this. So you have a network, and then you have generator G1, generator G2, and then load L1, load L2. So there may be like this L3. So there are a lot of loads, a lot of generators. Now load is known. So 500, 200, some 600 megawatt. Okay. So 7 plus 6, 1300 megawatt. Is that? Yeah. So total load is known. Okay. So which generator should generate how much? So now I will say that the cost of this generator is, let's say, this is using a certain type of coal, and the cost is, let's say, 3 rupees per unit or kilowatt, something like that. So this much power to generate, it will take 3 rupees, and then this one, let's say, 6 rupees. So obviously your answer is that use G1 generator and generate the entire 1300 megawatts, so that your cost is less. But the problem is, there in the network there is some line. Okay, so line number, let's say from 4 to 6. So this particular line is getting overloaded. So because that line is getting overloaded, you cannot generate even though it is less cost. Then what will you do? Then you reduce this one and increase the generation at G2. And then maybe because of that this overload is reducing. Okay. So usually if there is a cheap low cost generator, the lines near to that generator are getting overloaded. So because everybody wants to get the power from the low cost generator. Okay. So this can be given as a formulation of an optimization problem, and then solution can be. So what will be the constraint? So what will be the constraint for this one? So the constraint will be like this: the power flow less than or equal to capacity for each line. So power flow in line I less than or equal to capacity of line I. So this will be your constraints. Okay. Yes. Okay. So the question is, you use less material and you get the 2000 capacity, 2000 centimeters cube capacity. So what will you do in this case? What? Okay, surface area. So let's again call it A. What is the surface area? So pi r square into 2. So this is the bottom and top. Pi r square into 2 plus 2 pi r h. So 2 pi r is this one and h is the height. So this one. So this is the surface area of a cylinder. Okay. So this you want to minimize. So I'll write MIN. Minimize this quantity. So what is the constraint? So pi r square h less than or equal to, so greater than or equal to, okay, greater than or equal to 2000. But then since if it is, it's already understood that it will be equal to 2000 because you want to anyway reduce the amount of material used. So strictly speaking it should be greater than or equal to, but then since we already know that it will be equal to, so I can write it like this. So what is the next step? So this we have formulated. Now how to solve it? So what do you want to do? H equal to 2000 by pi r square and then A equal to 2 pi r square plus 2 pi r into 2000 divided by pi r square. So pi cancel, r will be like this, this will be 4000. Okay. So what is the next step? So one variable, so dA by dr. Okay. So this will be 4 pi r and this is actually 4000 by r. Okay. So what is the derivation of this? Minus 4000 by r square, is that correct? Okay. This should be equal to 0. Okay. So are we doing it correctly? So what is the next step? So what? $4,000. So r cube equal to this one, r equal to by 4 pi or cube root of 1000 by pi. Okay. So can someone try this? Will we be able to find this one? Cube root of, at least we can verify your calculators are working correctly or not. 6.8 centimeters. So this is my radius. So height will be, you can calculate that. So if you make the cylinder with that, with less area, I can cover the 2000, this one. So what is the height? Just to get the idea. How much is the height? 2r, why 2r? 2000 divided by pi r square. No. See, 2000 divided by pi r square. 13.3? 13.7? So somebody said the height will be 2r. It's around 2r. $13.6 is 2r. So this might be something here. So and that the 2r relation will continue, whatever value of this one. So how do you prove that? Yeah. Yeah. So it will be cube root of, v by 2 pi, something like that. cube root of v by 2 pi. So anyway, so okay, I think I'll move forward. So whatever we are doing so far, we had two variables, but then you substitute one variable and then eliminate the other one, and then you are able to solve it. Okay, so let's quickly do one example of a problem having two variables and then you are not substituting anything. So there is a plane given by x minus y plus z equal to 3. Okay. So this is the equation for this plane, x minus y plus z equal to 3. So it represents a plane in x, y, z, and there is a point. Okay, let me see the coordinates of that. So 1, 2, and minus 1. Okay, so I want to find out what is the minimum distance between this point and this plane. Okay, so again, how will you do that? So this is a point and then this is a plane. So somewhere there is a, so let's assume that it is x, y, z. So x, y, z is unknown. Okay, and I want to minimize the distance from this P to this point, and this point satisfies. So already I can write this constraint right away. This should be satisfied, which means that xyz point is already on this plane, and the distance will be x minus 1 square plus y minus 2 square plus z plus 1 square. Okay, because there is minus 1. So this I am not putting the overall square because I'll say d square, and then I want to say minimize. Okay, minimizing d square is equivalent to minimizing d. It is easier to work out. So now what you can do, even if I substitute, now if I say z is equal to what? Yeah, 3 minus x plus y, and this one will go here, so this 1 will add and it will become 4. So I can write it here, x minus 1 square plus y minus 2 square plus 4 minus x minus y plus y square. So even if I eliminate one variable, I have another variable. So what is the next step here? What is the next step? Okay, yeah. So let's call this f. So df by dx, and then df by dy. Okay. So this is actually gradient of f. So what is this? Take the first one. What? Yeah, correct. So 2 into x minus 1. So this is constant. This is, here I will get minus 2 into 4 minus x plus y. Okay. So this one, it will be 2 into y minus 2 plus 2 into 4 minus x plus y. Okay. So these two should be zeros. So why it should be zeros? Because at the minimum point or maximum point, the gradient will be 0. So if you look at, so we have two unknowns, two equations. So 2x minus 2 minus 8 plus 2x minus 2y. So 2 to 4x minus 2y minus 10 equal to 0, or I can write it 2x minus y minus 5 equal to 0. I hope this is correct. So I am writing one equation, 2x minus y minus 5 equal to 0. Okay, what about the other one? So this is 2y minus 4 plus 8 minus 2x plus 2y. So I'll cancel all the 2's. So y minus 2 plus 4 minus x plus y. So y is 2y minus x plus 2. Okay, so minus x plus 2y plus 2 equal to 0. Okay, so I'll multiply by 2 and then add them. 3y minus 1 equal to 0. Okay, 1 by 3 and x is, okay, I'll just write it. Then z also we can know. 2 by 3. So this is a point. So that point is this values we got. So at that point it is, the distance is shortest. Okay. But how do you know it is shortest? You have to take the second derivative. Okay. So what is the second derivative in this case? So the second derivative will look something like this. So it is represented as j. Again, j is Jacobian. That is the name of the person who has suggested this. So how will you get the derivative? So this is dou square f by dou x like this. Dou y dou x. Okay. So let's quickly do that. So this is with already with x. So again with x. So or we can try this one. So it is 2. Okay. So say 2 times if you differentiate with x, you will get 2 or what? So here you will get 4. Okay, 4. We'll do here itself. So this one differentiate with y minus 2. This one differentiate with x. How much? Minus 2. And this one differentiate with y 4. Okay. So this is your matrix of second derivatives. But then how will you tell it is maximum or minimum point? Is it the shortest distance or longest distance? So you have, so you have to find out the what is called as whether this matrix is positive definite or not. So you take the first part. What is the determinant? D1. D1 is 4. Now you take the second. What is now the determinant of the overall this thing? D2. So AD minus BC. So AD minus BC. So which is coming 12. So this is positive. This is also positive. Okay. So if all the determinants are positive, then the overall matrix is positive definite. Positive definite. That means you are at the minimum point. Positive means minimum point. That means the distance is shortest distance. Okay. So if all of them are negative, then it is negative definite. That means the point is longest distance. I mean for a different function, for a different problem. So for you can think about something like this. Like there is a circular. Your fort is in the form of circle, and then somebody is coming to attack you. Okay. So if somebody is coming to attack you, you want to go to the opposite side, or if you want to attack, you want to come here. Okay. So this distance, the all equations will be same, but then this point correspond to the minimum distance, this point correspond to the maximum. You will get two solutions or something like that. Anyway, okay. So that was what will you do if you find that one of the determinants, like not all of them are positive, some of them are negative or something like that. Then it is indefinite, and your point also, whatever answer you are getting, that answer also indefinite. You cannot say it is positive or negative. Okay. Okay, now I think maybe last two problems that we'll do today. Uh, So all this trick of substituting and then solving and all may not work out all the time. So you might need some different methods also. But then now the problem is something like this. Let's say there is two pipelines. So this pipeline is A. So let's call this. Let me draw like a pipe. So this is A and this is B. Okay. So let's say this distance is a very long distance. Okay. So the cost of, let's say there is a oil here, and then you want to send the oil from this side to the other side. Like there is some kind of a refinery, and then you want to transport it. So the cost of transporting here is 4 into x square. Okay, where x is the amount of weight of the oil or whatever amount of the oil, and the cost on this is 4 into or 6 into y square. Okay. So what is happening is so total is x plus y. That x plus y, you are separating this side x and this side y, and then you are transmitting through this pipeline, and then here you are receiving the total x plus y again. Okay, but the problem is cost is 4 into x square, and here the cost, where x is the amount of oil here, y is the amount of oil here. Yeah, by weight or by volume or something. So let's say x plus y is let's not use big number. Let's say 1000 barrels, something like this. 1000 barrels of oil you have. Sorry, 100, not 1000. 100 barrels of oil you have, and you want to do like this. Okay. So what is your answer? How we should? What should be the x and what should be the y? What? Okay, let's get some graphical interpretation. So if you consider x and y, so one solution is this one, 100, 0. Other solution is 0, 100. Okay. So here all the oil is going on x, and here all the oil is going on y. Okay. So do you think this is the answer? Because one is 4x square and the other is 6 into y square. So do you think 0, 100, 0 is the answer, or no? It will not be the answer? 6y square is better? See, I want to reduce the cost. So this is the cost, right? So this is the cost. This is also the cost. I want to reduce the cost of transporting. Maybe. Okay. So, is it not that you send everything on one side and then?
But actually, we are missing the parallel part.
But the cost is more, right? Yeah. So if I make it y equal to 0 per barrel, let's say, the unit is barrels. Okay. So what? No time constraint. Maybe this is barrels per day. Every day you want to send it. So how much is the? Then send everything on pipeline A. We can calculate actually. So what is the cost in this case? 4 uh, 4 uh, 4 into 100 square, isn't it? 40,000. Okay, 40,000 rupees is the cost. So let's take one point here, which is 99 and 1. Okay, so what is 4 into 99 square plus 6 into 1? Okay, what is this one? 4 into 99 square plus 6 into 1. 3070. Okay, one answer is 3070. So XY. So what I am trying to do is I just take one step up. Okay, how much is the cost? How much is the 39210? See, the cost here is 40,000. The cost here is only 39,210. So 790 rupees you are saving. Okay, so this point is better than this point. Like that, you will find, you keep going, you will find this one. And what about this answer? This is 6 into y square, so 60,000 rupees. So 40,000 and 60,000, but in between it is reducing and then increasing. 60-40. Okay. So this you are suggesting as a correct answer. But then how did you solve it? Okay. So another way of looking at is look at the cost. So 4x square plus 6y square. Okay. This is a function. Okay. If I say equal to 40,000, what does this represent? This represents an ellipse. Okay, and that ellipse will be passing through this point and all. So it will be coming something like this. I'm bad at drawing ellipse. This ellipse represents 40,000. Okay, so which is the ellipse which represents 50,000? It will be slightly outside like this. This is the ellipse which represents 50,000, and this is the ellipse which represents 60,000. Okay, and then maybe this is the ellipse which represents 10,000. So this here there will be a tangent. So here it is intersecting at 2 points. So we want a intersection only 1 point. This is intersecting at 0 point. So this point is the solution. Okay. So what is the condition that it is a tangent? The slope of the ellipse. So this is the ellipse. Okay. Slope of the ellipse should be equal to the slope of the line. So what is the slope of the line? X plus y equal to 100. Okay, this is the constraint. X plus y equal to 100. This is a straight line. What is the slope of this line? Slope is exactly not the right this one. We'll use this one. Gradient. Okay, of let's say let's represent this as L. So gradient of L is what? So 1, 1. What I'm saying is, see, dl by dx, dl by dy. Okay. So differentiate with x, you will get 1. Differentiate with y, you will get 1. So 1 comma 1 is your gradient. Okay. So that is the gradient. So let's use it. Gradient of L, 1, 1. Okay. And what is the gradient of the this one? So again, del f. Okay, gradient of this 8x 12y. Okay, so this is the gradient 8x 12y. Differentiate with respect to x, differentiate with respect to y. Now this is in a certain direction, and this is also in the, so both the directions should be same. both should point in the same direction. Okay, so this gradient of f and the gradient of L should be matching, and you should be multiplying just by a constant. So what I will do is 8x 12y equal to c into 1 1. So 1 c and c. So c is a constant. Okay, so in this case you will get c equal to 8x. So I can put here. So 12y equal to 8x, and therefore x by y. So using that you can solve. So 4 3's and 4 2's. So you will get 3y equal to 2x. So yeah, that one 3 into 40 equal to 2 into 60. So this is satisfying that. Therefore, this is your answer. So this point will be 60 40. Okay. What is the yes? That's what we had done. So how will you get the slope here? Differentiate.
y with respect to x. So it will be 8x plus 6 into 2y divided by x. And the divided by x is minus 1.
So what you are saying is 4 into x square plus 6 into y square. So
8x plus 12y into divided by x.
8x plus 12y into dy by dx is equal to 0. But then why you want to make it equal to 0? I don't know. I'm not getting the shortcut what you are trying to do. Okay. This one. Other side is constant. Okay. Oh, okay. The derivative of 40,000. Okay. So okay, the dy by dx here. So and the dy by dx there, you want to equate. Yeah. 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 So but then I think that it is coming like this because it's a two variables thing. So if you have more variables, you will find gradient. So fair enough. So what is the answer? By the way, how much is the cost? So 60, 4 into 60 square plus 6 into 40 square. How much is this? 4 into 3600 plus 6 into 1600. 24,000. So see how much less it is. So here it is 40,000, here it is 60,000, but in between here it is 24,000. Is 24,000 correct? Okay, looks like correct. Okay, now I'll ask you another question. Okay. This is a current source, not a voltage source, and the current is 100 amperes. Okay. And there is network is like this. So this is I1, I2. Okay. Find I1, I2 without Ohm's law. So don't use Ohm's law and find out what is I1, what is I2. Yeah, so 40 I1 equal to 60 I2 is application of Ohm's law. Without no, suppose you don't know Ohm's law, and then I ask you to solve this problem. So, so the question is why minimum, but then at least we'll try his approach. So I'm hearing one answer is let's find out this one. So how do I proceed now? Okay. So power loss here is 40 I1 square plus 60 I2 square. Okay. By the way, to match it to the exactly the previous problem, this should be 4 ohms and this should be 6 ohms. So let's do that. So no, we don't use Ohm's law. How much is the power loss in this? See, what is the power loss in this one? If I don't have to know Ohm's law to find out how much is the power loss. See, what I'm saying is that if I want to know what is the total power loss, so it is this one. This is the total power loss, and if I minimize this, it turns out that the if you have if you remember that this one grade f equal to all that, we got what? We got 8x equal to 12y. Okay, this is a form of Ohm's law. So taking derivative, equating to 0, that step is Ohm's law actually. So 8x equal to 4y, what we were getting before. You are taking like, so differentiation with I1, differentiation with I2, you will get 8x, 12y equal, both are equal kind of thing. So you will get the Ohm's law of that. So anyway, what happens is nobody, see, now the question comes like this. I go to a lab and then I take the 4 ohm resistance, 6 ohm resistance and I connect it, and then I connect a 100 amperes current source, and then I measure the current and I'll wait. So somebody, whoever is there, somebody is calculating this optimization problem, taking a decision that okay, let us send 60 amperes in this branch and let us send 40 amperes in this branch, and then it is coming out in the lab like that. So the question is, who is doing that calculation? So as a student, we can calculate that and find out this is 60 amps, but in the physical world, when you connect the circuit and when you what? Yeah. Yeah. So yeah, so that you are answering your own question. Like you are asking him why it should be minimum. So somehow it turns out that in the physical world or in the nature and all, automatically some things are getting minimized, some things are getting maximized and all. So that one. I think we still have some time. I just want to look at one problem. Then okay, so now I'll just quickly work out one slightly bigger problem with different types of constraint. Okay, before going that, I want to also tell you one more thing. Let's go back to the same problem. Minimize 4x square plus 6y square x plus y equal to 100. Okay. So I just want to tell one more way of solving it. It's called Lagrange function. So what happens is, this is a objective function, this is a constraint. Some cases you can replace, like you can say x equal to 100 minus y, substitute it and then do it. But some places the substitution may be more tedious, like if you have a more complicated function, the substitution may be difficult. So easier method may be different. So in this case it is good, we can substitute 100 minus y and then you can do that. But how we can do with the Lagrange function is something like this. So you can write one more Lagrangian function with variables x, y and lambda. So this lambda is a Lagrange multiplier, like that we call it. So what you will do is, you take this one as it is. So 4x square plus 6y square. Then you put a plus mark and then multiply this and then this entire one. So you take the 100 on the other side and then equal to 0. You make it equal to 0 and then here you can put x plus y minus 100 equal to, that's all. So this whole thing is a Lagrange function. Okay. So this is your given function. Let's call it f of minimize f of x comma y. So somebody has given you 2 variables and 1 constraint. So it will become 3 variables. So if there is another constraint, then I will get lambda 1 for this, lambda 2 for this. So like this. Now you write a function like this. Now the next step is you minimize this function. So minimum of this is equivalent to minimum of this. Both problems are equivalent. So if I want to minimize this one, what I will do? So dl by dx, dl by dy, and then dl by d lambda. Okay. So this is the Lagrange method. Okay. So if I differentiate with this x, I will get 8x plus lambda, and then here I will get 12x plus lambda, and then here I will get x plus y minus 100. Okay. So now all of this should be equal to 0, 0, 0. So I have 3 unknowns and 3 equations. Okay. So if you solve these 3 unknowns and 3 equations, you will get again same thing, x equal to 60, y equal to 40, and what will be the lambda? 12 into 60. No, it will be some value, I think. What will be lambda? Oh. No, see, 12y plus lambda equal to 0, lambda equal to minus of 12y. How much will that be? 12 into 480. Okay. With a minus sign. What? You have to solve it. Because I just, if you solve it, it will come like that. I have just put directly to save some time. So if you solve it, see here what you can do is x equal to lambda by 8. So minus lambda by 8 plus, so minus lambda by 12 equal to 100. Okay, so like this if you solve, so will we get minus 480? I don't know. Anyway, you should get minus 480. So what is the new thing that this Lagrange function method is telling is, we are introducing a new variable lambda and then putting a constant here and then solving it. But my question is, what does this 480 signify? So this could be 480, this could be 420, this could be 900. So what does the magnitude of this number signify? What? What is the significance of this quantity 4, or what information do you gain by looking at this 480? So what is the significance of your Lagrange multiplier, value of your Lagrange multiplier? What? Weight of constraint, okay, that is one word for it. weight of constraint. So what do you mean by this? Weight of constraint. Okay, how much, so how much effect on final solution? Okay, so this is the meaning of weight. Okay, so what is our final solution? Final solution in our previous problem was the cost of transporting the oil. Okay, so what was the optimal cost? Optimal cost. What was the optimal cost? 24,000 rupees. So this was our optimal cost. Okay. So now what does this 480 signify? So how much effect on final solution? So are you getting some clue from here? Instead of sending 100 barrels of oil, suppose one of the days 1 barrel of oil got extra. So I produced 101 barrels of oil. Okay. So now I want to transport. So my cost will increase by 480. So it will come 24,480 rupees. Okay. So my cost will increase by that amount. Or if it is only 99 barrels on one day, my cost will decrease by 480. Okay. So what? Yeah, when you actually solve the optimization problem and everything and all, your solution will be differing with that number. Okay. So how is that important? So that is important because if somebody comes and then says, I have a small bicycle and I can carry 1 barrel of oil on behind of my bicycle and then I can go. Okay, instead of A and B, you have a third path on a cycle. One guy can take this one, but he is asking 600 rupees. So you will say it is not optimal. So as long as the cost is less than 480, if you pay him only 300 rupees, so otherwise to transport in your regular means A and B pipelines, it would cost you 480 rupees more. So instead of that, if you have an alternative guy who can take it for 300 rupees, you will earn you will get a profit of 180. So in fact, what you can do, you can reduce your regular flow, like instead of 60 and 40, so maybe this 40 you will make it 30 only, because it is on Y. So you make it 30 and 39. Okay. So one you reduce and then send it to other guy who can take it for this one. So if what you are asking, if it is 2, then yeah, I think for this problem it is 2 times because it is square function. So something like that. So maybe just to summarize the discussion, if I write it like this, see, my x plus y plus g or z should be 100. So where z is the amount I am transmitting on that guy who is at the cycle, and then x plus, so this z should be equal to 1 or less than or equal to 1, and then what is my cost? So I will say 4x square plus 6y square plus z into 360. Sorry, z into 300. So let's say the guy is charging only 300 rupees for 1 barrel of this one. Now if you solve this entire problem, you will get that z is equal to 1. Okay. But if you make this value more than 300, so if you make it 500, so more than 480, then your less than or equal to, it will still, z will be still 0. We'll say instead of using this other one, we can still send it on the regular thing. Anyway, so in Microsoft Office, you can actually solve this kind of problems. You can create a spreadsheet, and in one of the cells you write this equation. So what you do is maybe this one you keep the value of x, and y you designate another value. Then your cost you create an equation, this square into 4, something like that. You create the equation. Then there is a you can define the constraints. You can define all the things, and there is something called sensitivity report that is generated in the Microsoft Office Excel, and this number it will also display in that report. So that will be useful for this kind of things. In fact, if you, let's say if there is a company and then they want to take a new employee, okay, how much salary they should pay. So the incremental, so how much increase in the profit is coming, less than that they want to pay the salary, so that company is also getting some profit. So that 480 number is that one. So that is the importance of that Lagrange multiplier lambda. I think maybe I can see from here. So I don't know whether we'll complete this. I'll just start this problem and then I'll leave it to x squared. I think I'm writing. So let's say that this problem is given. This function you have to maximize. So these two constraints are given to you, okay, and then yeah, so maximize. Last one more constraint is there. Nothing. Okay. First of all, forget about this one. Just look at this 4. Okay. So if you take, yeah, it is in between 2 and 8 hands. So if you take the 2 minus x less than or equal to 0, 2 minus x less than or equal to 0, that means what? So plus x plus x. So x greater than 2. Okay. So this region. So this right side region. Okay. This is 1. 5 minus y less than 0. That means what? 5 minus y less than equal to 0. 5 less than or equal to 5 minus y less than equal to 0. That means y greater than 5. Okay. So I'll get something this area. Okay. Let's look at the last one. X minus 8 less than 0. So x less than 8. That means somewhere. This one. So this region. So I am getting this 3 now. And then what is that? X plus y minus 20 less than 0. So x plus y less than or equal to 20. Okay. So something like this it will come. Okay. So if to summarize it, I'll get something, an area like this. Okay. So this is called feasible region. Okay, this is my design variable x and y. So this is my feasible region. Okay. Now look at this function. This is something like a ellipse. Okay. So which is not straight on x and y because x into y is there. So it will be something like this, some function like this maybe. So I am drawing some values like this. So this will be like equal to k. So the k value, if you keep on increasing, you will get some things like this. Okay. So, but your solution should be somewhere inside this itself. So, so if the k value is increasing and if you want to maximize, then this point will be your answer. And if you want to minimize, then this point will be your answer, something like that. Okay. So, I just try to draw the picture for this problem and it looks something like this. So, what is the best way of solving it? So, if you notice the constraints, okay. If your solution is here, this one is, let's give it numbers, let's call it H1, H2, H3, H4, okay, 4 constraints. So, this one is H3, this one is H4, this one is H2 and this one is H1, okay. So, the answer, by general observation, you can say that answer is either here, here, here or here, okay. Usually the answer will be at the corners and again you can design a problem in such a way that the answer is in between. Like this point, if it is in between, then the answer is in between, okay. Or you can design a problem that this is exactly matches and the answer can be anywhere on the line. So those special conditions are apart. The answer will be somewhere on the 2 points, okay. Suppose you consider that H3 and H4 are the intersection points, okay. In that case, I can replace this whole thing. This I can replace like this. I'll say I'll call it G3 and G4, and G3 I will write x plus y minus 20 is equal to 0, and then this one I'll write x minus 8 is equal to 0. So I replacing the inequality constraints with the equality constraints, assuming that G3 and G4 are the solutions, okay, but I don't know. So I might, if I take only, so from here I know how to solve. Suppose if this problem is only given to you, how do you solve this problem? So you will write like this, lambda equal, L equal to same, x minus y plus 2x square plus 2xy plus y square plus let's say lambda 3, just name, into this one, x plus y minus 20 plus lambda 4 into x minus y, x minus 8. So now how many unknowns are there? 4 unknowns are there. 1, 2, 3, 4. So you will get 4 equations. So that is d lambda with x, y, lambda 3 and lambda 4. 4 unknowns, 4 equations. If you solve it, you will be able to find it. All of this is true, assuming that this is the optimal point. Okay. So, so for this, so for solving a problem with unequal constraints, that is the difficulty, that is the complexity. So we will not go into more details. So, but I want to talk about one concept that is called, I think it is called complementary slackness or something. So, see, how do you solve this trick? Okay, how do you solve this problem? So what you can do is, what I'll do is I'll rewrite this. I'll say 5 minus y, because it is less than or equal to 0. So this is less than or equal to 0. I will put some u1. Okay, what should be the sign of u1? So I'll say minus. Okay, or should it be plus? Yeah, so plus u1. See, because this part is less than 0, so I am helping it add someone and you reach to 0. So this part is less than 0, therefore I add some number to reach to 0. Similarly, this one 2 minus x plus u2 is equal to 0. Okay, this one also same x plus y minus 20 plus u3 equal to 0. Okay, and then x minus 8 plus u4 equal to 0. Okay, so u1, u2, u3, u4, these are called slack variables. Okay, slack variables. So what is slack? Slack is something extra. Okay, so if you want to eat 6 chapatis and your tiffin box has 8 chapatis, then 2 is your slack. So some extra is there if suddenly some emergency is there. So something like that. Okay, so these are slack variables. Now sometimes you might use it up, sometimes you might leave it like that. So now in this case H3 and H4 are what is called as binding constraints. Okay, if the solution is exactly at equal to 0, in that case H3 and H4 are binding. In that case U3 and U4 will be 0. Okay, so I will write it: if constraint is binding, then slack equal to 0. Okay, if that particular constraint is binding, then the slack will be 0. So by the way, if you want to write the Lagrangian function, what will you do? Lagrange function x, y. Now you have u1, u2, u3, u4. You have lambda 1, lambda 2, lambda 3, lambda 4. So this many unknowns you have. Okay, and I am not writing it, so it will be something like f of xy plus lambda 1 into 5 minus y plus u1, something like this you will get. Okay, I am just writing for example the first one. So this whole function, then you will have how many? 8, 10 unknowns, 10 equations, you have to solve it and then you will get it. So normally this is not a very big problem. If you actually go to some industry level problem, these things is actually very small. They have like thousands of unknowns and thousands of equations and all. Where was I? Yeah. So this statement is quite interesting. Maybe not in this course, but if you are continuing in the engineering field, so somewhere, sometime again you will see this. If the constraint is binding, then the slack is 0. And the other is if constraint is non-binding, okay, then slack is not equal to 0. So anyway, there might be a special exceptions to this, but then in general this is the case. So this is called complementary slackness. What about the lambdas? So here the Lagrange multiplier, lambda will be greater than 0 and here lambda will be equal to 0. So again, or I will say lambda not equal to 0, depending on a maximization or minimization kind of problem. So again, this is important interpretation. So what happens is, some time back we discussed that the oil production is 100, okay, and suddenly if I increase the production of oil, how much cost will increase? Okay, so there are some constraints which will directly affect the solution, like the equality constraints, but there are some constraints which may not affect the solution. So for example, we got a region like this before. Okay, suppose this is the solution. This one is what? This one is y 5 minus y greater than or equal to 0. So instead of 5, if I make it 4, it will not affect the solution. So because it will just increase the region here, but your final solution is this itself. Okay, so those constraints which are not binding, if you change them, they will not affect the solution. So what will be the Lagrange multiplier for that? It will be 0. So because what we defined Lagrange multiplier 480 that we got before, that is the amount it will affect the overall function. Okay? This will not affect the overall function. So if there is slack, then this one is 0. So if there is a slack, then if slack is not equal to 0, lambda equal to 0, and if lambda is not equal to 0, slack equal to 0. So something like that. Yeah, again, this is a broader optimization point that you might see in different other problems, other fields. So with this, today I just gave the brief. Actually, it is again, as I said before, optimization is a one full semester course. So we just try to see some trailer of that optimization today. So, but then that is okay for going to the next next class. So, yeah, that brings to the question, when will